Welcome to this explainer. Okay, so if you've ever opened a math book, spotted the word logarithm, and instantly felt that familiar knot of anxiety in your stomach, take a deep breath. Seriously, you are absolutely not alone here. Math can be incredibly intimidating, right? Especially when it looks like a completely foreign language. But I'm going to make a promise to you today. By the time we finish this explainer, this topic isn't just going to make sense, it's actually going to feel incredibly satisfying. We're going to take things slow, step by step, and I'll be right here guiding you through the whole shebang. And just to reassure you that we've got a super clear path ahead, here's our exact roadmap for today. We'll start with math in real life, then seeing the math first, the logic behind the formulas, solving step by step, common exam mistakes, and finally, we'll wrap up with the ultimate cheat sheet.
All right, part one, math in real life. Where do we actually use this stuff?
It's the classic, totally valid question every student asks, isn't it? When will I ever actually use this in my real life? Well, having the answer to that is kind of the secret to making the math stick in your brain. Logarithms aren't just abstract symbols. They're literally the invisible engines powering our modern world. When algorithms calculate compounding shopping discounts, they use logs. When surveyors measure vast scales of land or architects design buildings to withstand earthquakes on the logarithmic Richter scale, they rely on this exact math. Even the data compression that lets you stream high-quality video on your phone without eating up all your storage, that's all thanks to the principles of logarithms. It's real, practical magic.
Number 2, seeing the math first, the shape of growth. So before we memorize any rules, our brains really need a picture. We need to physically see what exponential growth looks like so we can actually understand the problem logarithms were invented to solve in the first place. Think about the brilliantly simple curve of the exponential function, y equals 2 to the power of x. As the value of x increases along the bottom axis, imagine what happens to the curve. It shoots upwards incredibly fast. Now notice point Q on that growth curve. It marks a very specific, kind of awkward spot where the y value is exactly 5.
And that brings us to our primary problem. If our equation is y equals 2 to the power of x, for which exact value of x does y become 5? Well, let's think about it. We know that 2 squared, 2 to the power of 2 is 4, and 2 cubed is 8. So the power that gets us exactly to 5 has to be some messy decimal somewhere between 2 and 3. But how do we find it exactly? Our basic algebra tools kind of fail us here. We need a new tool. We need the logarithm.
Moving on to part 3, logic behind the formulas, exponents in reverse. Okay, let's dive into this. This is where we uncover the core logic of why logs even exist, and I promise you, it's way simpler than it looks. If we compare these two functions side by side, on the one hand, we have the exponential function we just talked about, y equals 2 to the power of x. If we plug in an x value of -2, our output y is 1/4. Now check out the other side. This is the logarithmic function. If our input y is 1/4, our output x is -2. The inputs and outputs literally just trade places. That's the big secret here. Logarithms are just exponents in reverse. They're basically asking the question, to what power must I raise the base to get this number? Because logs are just reverse exponents, they follow the exact same logic. Introducing the product rule. It states that log base a of x times y equals log base a of x plus log base a of y. Why? Well, think back to basic exponents. When you multiply numbers with the same base, what do? You add their exponents, right? So naturally, multiplying inside a logarithm simply means adding 2 separate logarithms outside. Makes perfect sense. Now let's see how this builds into my personal favorite, the power rule. This one states that log base a of x to the power of n equals n times log base a of x. It's this incredibly satisfying trick. That little exponent n sitting up high, the logarithm allows it to simply drop down to the front and become a regular multiplier. This is exactly how logarithms take terrifyingly huge numbers and make them totally manageable. Section 4. Solving step by step. Easy, medium, and hard. We have our tools. Now take a deep breath. We are going to apply these rules one simple logical step at a time. Here is our easy example. Find the value of x if 2 to the power of x equals 3 to the power of 5. First, we identify what we are actually given, an equation where the unknown x is trapped up there in the exponent. And what is asked? We need to get x by itself on the ground floor. Watch how beautifully these steps unfold. Step 1, we take the logarithm of base 2 on both sides, just to keep things balanced. Step 2, we use that awesome power rule we just learned. The x drops down to the front on the left, and the 5 drops down to the front on the right. So we get x times log base 2 of 2 equals 5 times log base 2 of 3. Step 3. Okay, here's a wonderful shortcut. Log base 2 of 2 is literally just asking 2 to what power equals 2. The answer is 1, so that part just turns into a 1 and completely disappears, leaving us with our final answer, x equals 5 times log base 2 of 3. Fantastic. Now let's try a medium example. Expand log of 343 divided by 125. What are we given? A logarithmic expression containing a fraction. What's asked? To expand it out completely. Now I know what you might be thinking, this looks messy. It looks like a terrible fraction. But don't worry, we're just going to use our division rule, the quotient rule, to crack it right open. Step 1. The quotient rule tells us that division inside a log becomes subtraction outside. So this splits into log 343 minus log 125. Step 2. We convert those big numbers into powers. 343 is just 7 cubed, and 125 is 5 cubed. So now we have log of 7 to the third minus log of 5 to the third. Step 3, we bring back the trusty power rule. Those little 3's drop down to the front. Our final expanded answer is 3 times log 7 minus 3 times log 5. See? It's a very clean, super satisfying process. All right, now for a hard board exam level question. Solve 3 to the power of x equals 5 to the power of x minus 2. What are we given? An equation with variables in the exponents and completely different bases. What is asked? To isolate and solve for x. Now what makes this scary is that we have an x trapped in the exponent on both sides of the equation. But we can totally tame these different bases by using common base 10 logarithms on both sides. Let's do it. Step 1, we take log base 10 on both sides. Step 2, use the power rule to drop those exponents down. We get x times log 3 on the left and the entire expression x minus 2 times log 5 on the right. Step 3, we expand the right side. We just distribute that log 5 into the bracket exactly like we would with a normal number. So it becomes x times log 5 minus 2 times log 5. We are so close to the finish line. To solve for x, we just need all the x terms on one side. We group them together to get x times the bracketed expression log 5 minus log 3 equals 2 times log 5. Finally, to get x totally alone, we just divide by that bracketed expression. Our final answer is x equals 2 log 5 divided by log 5 minus log 3. Celebrate this victory. You literally just proved that even intimidating board exam questions fall apart when we simply follow the steps patiently. Number 5, common exam mistakes. Now that you've got the skills, I want to make sure we protect your grade. High-pressure exam environments can completely play tricks on your brain, so let's look at the most frequent traps students fall into. The absolutely crucial point is understanding where the math actually happens. The correct way is this. Division happening inside a single logarithm splits into subtraction outside the logarithm. But here is the danger zone. Dividing two totally separate logarithms, like log of x divided by log of y, does not equal the log of x minus y. Never, ever mix up an operation inside the brackets with operations between whole logarithms. And finally, section 6, the ultimate cheat sheet. First of all, huge congratulations on making it through the hardest parts. You've seen the concepts, you've done the heavy lifting, and now it's time to lock in your confidence with a final tool you can use anytime. Here are your 5 golden rules. 1. A logarithm is just a reverse exponent. 2. If there's no base written, always assume it's a common base 10. 3, 4, and 5 are your product, quotient, and power rules. And here's your surprise verbal trick for exams. Remember, log base a of a is always 1. Whenever you see the base and the number match perfectly, use it to instantly erase huge, ugly parts of complex equations and simplify them to a 1. It is a massive time saver. So, we've covered a ton of ground today, and hopefully that initial anxiety has started transforming into real confidence. But before we wrap up this explainer, I want to leave you with one final thought. If logarithms are just exponents in reverse, and money in a bank account grows exponentially with interest, how might we use these exact rules we learned today to figure out exactly how long it takes for your money to double? Think about it. Once you grasp this math, it ceases to be a bunch of exam questions. It actually becomes a real-world superpower. Thank you so much for joining me today. Keep practicing, and I'll catch you in the next explainer.